Okay, without further ado, I give the floor to Maartin Hoogerland from the University of Auckland. Thanks a lot for speaking again at this very late hour in the night for New Zealand. And you will talk about your work on something that is, you know, a long things, which is the observation of two-dimensional or Anderson localizations. And okay, you have the Maartin, you have the floor.
All right. Well, thank you very much, Marcel. Thank you very much for inviting me for this conference. I was really looking forward to seeing you all in Arcachon, but I suppose this will be good as well. So I'm talking to you from New Zealand, where it's in the middle of the night. So if I seem a little incoherent, that's probably why that is. I'm going to talk to you about this. Our recently published results on two-dimensional Anderson localization of ultracold atoms. This has been a project for me that took many years to accomplish, but I think that many people in the audience, like Alain, have similar experiences with these sort of experiments. A key part in this is also that we were able to have a research center of excellence in New Zealand that encompasses both the University of Auckland and University in Dunedin, Otago University, and so this collaboration was also really key in getting all of this to work. Right. So I'm trying to now go forward. Now I want to, of course, go to the next page, but this is not working.
Maybe you have to click on your image because maybe
there we go. Yeah. All right. So the outline is basically I'll talk about how the experiment works, talk about the results, and about the Gpe simulation that we have to help us interpret all of these results. And I'll say a few words at the end about localization landscape theory, which we felt was a good new direction to start really our understanding of how all of this stuff works. That's just following Marcel's great talk from yesterday. There's just a few new things in it. All right. So as I mentioned, our results are just recently published now in Nature Communications. It came out last Friday, so this is excellent timing for all of this stuff, of course. So this was a collaboration between us doing the experiments and the people at the University of Otago, led by David Hutchison, to do the Gpe simulation. All right, well, as this is a school, I thought I'd just put in a little bit of an introduction here. So we are going to be doing a two-dimensional transmission experiment, and we're going to be using a starry sky potential, so a binary sort of potential to avoid the percolation problems that you might have in 2 dimensions with a speckle potential. We have a projection system that eventually gets a minimum structure of about 1.4, 1.5 micrometers that we can project on our atoms. So if you just do a quick calculation there with this, if you want the structure to be similar in size to the de Broglie wavelength, then you get a kinetic energy of this of an atom like that should be in the order of 50 nanokelvins. Now it turns out that 50 nanokelvins is still way too hot to actually get this experiment to work, but you still essentially need a Bose-Einstein condensate to start with. Now in our experiment, interactions are not really important. And as the before actually entering this transmission channel, these atoms actually expand for a little while in the in a reservoir, and we have done well according to our simulations. In the simulations, of course, we can crank up the interactions to by whatever we like, and that doesn't seem to make any difference to change the interactions by a factor of 10. So this is by all means a single particle experiment. So of course, with the Anderson localization, what you have is that you have two possible trajectories to go from A to B. One on in my picture on the right, with a counterclockwise and a clockwise sort of path through this this disordered potential. These path lengths are both the same, and that means that the scattering back to your original point is actually interferes constructively, and that inhibits the transmission. So this is my sort of 1 second interpretation of how we actually get all this localization to work. And in 2 dimensions, everything is a little bit easier to see. Right. Okay. So we set up an experiment that looks approximately like this, where we have a reservoir. Our atoms start out in the reservoir on the right to make everything confusing, and they are propagating through a channel that has some dots in it that are bright. These dots are repulsive, and so atoms cannot. Well, they are certainly deflected by it, and eventually they go through to the reservoir on the left. So this is a little bit like these Atomtronics experiments that were already done by Esslinger and so on. Right. So our experiment looks, well, schematically a little bit like this. We have an all-optical Bose-Einstein condensate. That means that we just have CO2 lasers to create all of the trapping. Then we have a 2-dimensional pancake trap so we trap our atoms in these 2 dimensions, and in these 2 dimensions the atoms are free to move in principle, and then there is an extra structure projected on the top of it, just like you saw in the last slide. So yeah, I can't see my mouse in here, so there is this sort of blue-green laser signifies the repulsive potential that we project onto the whole thing, so it's a big beam with a hole in it with the shape of a dumbbell, and these little particles in the middle of the channel. And we'll do what I would call a transmission experiment. We'll just see how fast atoms move from one place to the other. Okay. Now, just a little bit of background about the experiment. This experiment we have had for a while. So it's a double mod system. We directly trap from the magneto-optical trap into a dipole trap without actually going through a magnetic stage. That does have its advantages in the sense that the experiment is less complex. The downside of it is that the number of atoms is always a bit limited. We typically get about 20,000 atoms of rubidium-87 into our Bose-Einstein condensate. So we have about 13 watts or so of light of CO2 laser light in each beam, and that gives a trap with a depth in the order of a millikelvin at maximum. So you do have to start with a magneto-optical trap, and you do have to start with relatively cold atoms, or things will just not get there. And so it takes 6 seconds of evaporation to actually get to BEC. Having a CO2 laser is really quite funny, right? It's like a heat ray. You can't see it if you push, but if you put any kind of body part in it, you do notice very quickly. So it's different from most other lasers, right? So and then eventually we get a BEC that looks like this after about 10 or 15 milliseconds expansion, and it has this typical kind of inhomogeneous expansion pattern. It's a little bit of an egg, and we can always easily distinguish it from the background, from a thermal cloud. Okay, so that's so then we have these atoms at 50 nanokelvins or so of residual energy, but this is not going to be cold enough. And of course, what we actually wanted to do was to use a two-dimensional experiment. So then we are going to lock everything up in a two-dimensional trap. So what we have chosen to do is to use a stack of pancakes. So we have a beam from a fiber laser, so it's 1064 nanometers. We split it into 2 beams. They intersect at an angle of about 6 degrees, and then we get an interference pattern like you see in this picture on the lower right. Whenever you image something like that, of course you also get some funny interference fringes from the front of the camera, the little window in front of the camera. That's hard to avoid, and you get that as well. But so we get this two-dimensional trap. We have a stack of two-dimensional traps, but the spacing between all of these traps is about 8 microns. And if once we make our BEC, the diameter of the BEC is about 1 micron, so it comfortably fits inside one of these pancakes. And so that's we can just select one of these pancakes to trap everything in. I wouldn't be able to tell you which one it is, but this does seem to work. Now, then what we do is we turn down the intensity of our CO2 laser at the same time that we actually ramp up the intensity of this 1064 laser. Now, of course, if you turn up this pancake trap at the same time, you can actually relax the CO2 laser trap, because the main function of the CO2 laser trap is to keep the atoms from dropping, right? That's where a big fraction of all of the power goes. And of course, once they are suspended by this 1064 nanometer trap, they're not dropping anymore. So we can relax it quite a bit before things become a problem. And so after we have sort of gently expanded our and relaxed our CO2 laser trap, we end up with atoms at about 5 nanokelvins of residual energy in this, and we can get a transfer efficiency of about 70% into one of these sheets of the pancake trap. And then, so that's then sets the scene. We have this degenerate two-dimensional gas. Of course, in 2 dimensions, it's not really a condensate anymore, but it's quite a cold gas as such. And the other thing that I was going to say about that is, yeah. So the blue beams in this picture here are these CO2 laser beams, and there's this one sheet that you have there. Now the good part here is, of course, that that because we trap everything in 2 dimensions, that means that we can have a high numerical aperture imaging of this repulsive potential on top of that, and everything's going to be in focus because it's all in the right layer, and we eventually get a trap frequency in the horizontal direction that is about 1 Hertz, and we get a trap frequency in the vertical direction, sort of across the pancakes, which is about 800 Hertz. Now, this 800 Hertz is much corresponds to a much higher energy than any other energy that we have in the system. So we consider this as a fully 2-dimensional experiment. Right. Then, of course, we need to project this arbitrary potential. And the way we do that is we have a spatial light modulator. Now, we started out with the spatial light modulator with the idea that we would use it as a phase modulator, and we would be able to use it as kind of a hologram. Now, this whole situation, it was a nice idea, but it did not work in several ways. One is that if you use a spatial light modulator in a way that the pixels are not completely on or completely off, that they actually all the pixels actually have a bit of a they fluctuate in intensity with the refresh rate of the pixel, and in our case that was 60 Hertz, and that means all these pixels, quite a lot of the light is actually going on and off with 60 Hertz. That's bad. The other thing is that we could just never get all the imaging to go exactly right, and we ended up with huge distortions that we could not get rid of. But if we use the spatial light modulator as just an array of a large array of quarter wave plates, that is fine, and we use it in this sort of double pass setup where you reflect everything off the surface of this spatial light modulator. And some of these pixels, the polarization gets rotated, and then it gets transmitted again by the polarizing beam splitter, and that gives us a very high. And that way we can have the pixels either on or off. It means we have no intensity fluctuations, and that means that we can have a very high contrast image. Now, in this picture B that you see here, we imaged some test gratings, and this is approximately the resolution of our imaging, really. Right, we have a lens inside a vacuum that has a numerical aperture of 0.42, and we reduce the size of this image on the spatial light modulator by a factor of 28 or so, and then we get to 1 pixel, is 0.7 microns in our image, and we use a 5-watt green laser to project everything on these atoms. So what does that look like? Well, yeah, but this is some tests that we did. So we have done some ray tracing that actually seemed to work just fine. We tested it all out with test gratings and so on to image those, and we see that if we try to make a 1 pixel grating, so 1 pixel on, 1 pixel off, that the contrast is really bad. But if we do a 2 pixel grating, the contrast is fine, essentially. The 2 pixel grating is here, and the spatial frequency of 0.7 per micron. All right, and we can measure this point spread functions and the like. All right, so then we did trap some atoms in different shapes. So we can do a cat like Schrödinger, or we can do a kiwi bird, the national bird of New Zealand. that is quite right. Then, so our experiment that we are doing is an Atomtronics experiment. We have an initial reservoir, we have a final reservoir, and we have a channel. And if we don't put anything in the channel, then you get this. Then you can look at the imbalance between the different between these different reservoirs, and the imbalance between reservoir 1 and reservoir 2, and that would just develop this kind of bounce like you see in this picture on the lower right. I'll get sort of speed up a bit to get to the to the interesting parts here. And so here we have our channel disorder that looks like that. And now these are some pictures that we have taken after long expansion times in our or long interaction times in these channels. So we have different levels of pixels in all of these. Now the height of one of these pixels is in the order of what was it, 5 nanokelvins or so to get across. Now, one thing that we did actually have to do is to have a little tilt on our two-dimensional trap, so that atoms would actually be encouraged to get into this channel. But we also made this work into. We also put this into the simulation, and in the picture on the top there, you see both pictures of the experiment and pictures from the simulation of that same experiment. So we see in the channel that once the density of scatterers goes above a certain value, that we get an exponential the channel density profile in our channel, and then of course we can measure the length of this apparent localization length as such. So in this case, atoms actually don't make it all the way through the channel. Right. We can, of course, this whole thing varies as a function of time, right? And we have taken many pictures after a long time, and so you see that everything sort of ends up at one particular point after a long time, after some oscillation. Of course, I said we could do a Gpe simulation of this whole thing as well. So here we start with a bunch of atoms here in our dipole trap. They essentially carry on this Gpe simulation while the trap is still there, and the trap gets turned off, and atoms sort of spread out into the channel just like this. So it's always very pretty with all the little nodes and antinodes and things. Unfortunately, we can't resolve all of these nodes and antinodes, but you see that atoms only make it a part of the way into the channel. Now, the Gpe simulation actually does give us some handy insights in what is actually happening. Right, we can actually, of course, in the Gpe simulation, you can measure what the momentum of all these particles at any time. You can see where they all are and so on, and that actually gave us quite a lot of insight in what was actually happening. So what was of course happening is that part of these particles is actually not localized. They have an energy that's too large to be localized by this particular potential, or the localization length would be too long. It would be outside the range of our experiment. So on the go up. Can you go back up? Yeah. we have, for instance, the picture B here is sort of the momentum distribution that we get from of these atoms in the source reservoir, according to the Gpe simulation. Now there is one particular momentum, of course, for atoms that would really be classically trapped just by the tails of the Gaussian little blips that we make the starry sky potential out of, and that's here indicated here with K threshold, KTH. So most atoms are actually warm enough that they are not classically trapped. Then on the in picture C, we see the localization length as we should be having it as a function of this K, of the wave vector of these atoms. And so we have a lot of atoms sort of in the range from 1 to 2, and we see that the localization length for those atoms is still acceptable for experiments. It still fits. It's still localized within about 100 microns, which we can easily see in our experiment. Then of course, you can measure the momentum distributions inside the channel and inside the source and so on. And we see that that only low K vector atoms are really trapped or localized inside the channel. Right. Now we can also have a look at this whole thing with this imbalance that I talked about earlier, right? This delta N, which was the population in one reservoir with respect to the other reservoir, and look at that as a function of time. And then this was our original sort of way of looking at it. So for a little bit more empty reservoirs, that seemed a little bit more empty channels, that seems to be a good way of looking at it. And then we end up with measuring the resistance of this channel in looking at this as an Atomtronics experiment, as we discussed earlier, where we have the imbalance be essentially corresponding to a voltage of driving atoms from left to right, and then the resistance in the channel is just essentially given by these by the disorder in the channel. The capacity of these of both these reservoirs is essentially given by the mean field in these two reservoirs. So here we have some results here where we can just plot the resistance as a function of the fill factor that we call eta. So that the fill factor of the channel is essentially the number of the ratio of the pixels that are bright compared to the pixels that are dark. And of course you see that that this resistance for a short channel remains quite lowish. For a longer channel, it goes up quite strongly. Right. Yeah. So of course I didn't do all of this stuff by myself. I'm just going to try to wrap this up a little bit. And these are my students Donald White and Thomas Hayes and Dylan Brown have done all of the work in the laboratory really, and the team in Otago with Mojde and Daniel have been doing the Gpe simulations. So our results are really that we have a two-dimensional experiment with ultracold atoms. We have slow atoms get localized in this channel. The faster atoms, they just get reduced transmission, and we get a good agreement with with Gpe simulations. Now I want to take 1 or 2 minutes to advertise our work on the localization landscape theory. Marcel, of course, gave us a very nice lecture on this yesterday. So the good part is that I don't have to talk too much. So we essentially started this work just to understand what we had been doing and how, just because some of these calculations that you may want to do to derive what the localization length is may be very difficult. So again, we are trying to consider solutions of an equation where HU equals 1, right? Where H is the Hamiltonian, U is essentially this landscape that we are trying to develop, and it turns out that it looks a little bit like atoms are moving in this effective potential that is defined as 1 over U. So these ridge lines of W are essentially values of U. And what I've drawn in the top right picture is essentially some of these ridge lines of W or valley lines of U, and of course in these valley lines, eventually or in these ridges, there's going to be some saddle points where there is going to be a low point where in principle particles can move or quasi-particles can move from one side to the other. Now we have some points here indicated somewhere in the big flat parts that are the minima of W, where we can say, well, in our approximation, what we're just going to say is our bunch of atoms just resides over there. Then, of course, Marcel was also talking about the Ekman distance to eventually look at the coupling between two of those valleys of W, and this Ekman distance is defined as we have here in the as the minimum of the integral of W minus E. Okay, so if W is so this is all energy dependent, right? And so if the energy of this particle becomes large, that means that some of these insurmountable sort of hills in W are going to disappear, and some of these domains are going to be joining together because of the ridge lines essentially just submerge under the water, as you would if the level E here is some kind of water level, and so that just joins these domains together. Now the sort of average diameter of the domains that we have at a certain energy we can call D. Now this Ekman distance is of course is a minimum of all these possible integrals, but the way that we have chosen to go about it is just to go along the lines of steepest ascent from one place to another, and so that seems to be give a very good idea of what this Ekman distance actually is. It's very easy to do. and that will give us a good number. And so then eventually we get to a localization length, which is just the essentially the size of the domain divided by this Ekman distance. And once you have that, that is relatively trivial calculation. Now our results are look eventually like this, where we have filled in some numbers. There is a so we have on the vertical axis we have this localization length. On the horizontal axis we have energy. As we mentioned, the energy here is that changes the size of the domains, right? And changes the Ekman distance. So and of course we need to scale it with respect to something, and so we scale it here with this energy E naught. So the fill factors we actually used before, and so L is what the typical length scale of the system. In our case, it would be about the diameter of one of these stars, or the size of one of the stars in the starry potential. Now there is some stuff happening when you go to large energy. At large energy, this system doesn't seem to work well. The red curve in this insetted there just indicates a lot of stuff that happens at large energy, but that doesn't seem to. I don't think that's real. That is just associated with the size of the problem getting too big, or the size of the domains becoming the size of the system that we are actually considering. Now, this is also not done by me. This was done by Sophie Shamailov, and this you can preview this work here on this archive paper that you have on the bottom here. So I think this localization landscape theory is really starts to give us some insight in what's actually happening in our localization experiments, and I really think this has a long way to go. All right. Well, with that, I would like to thank you for your attention, and any questions, please welcome.
Okay. Thank you very much, Maartin, for a very interesting talk. I'm sure there are questions already. Thomas. Okay, Thomas, you have.
Yes,
can unmute.
Start my sound already. Yeah, I have a question on. So in the end, I missed how much is actually the localized fraction that you see, and how much you have to rely on the comparison with Gpe simulation in order to assess it.
Oh yeah, well, there was a thank you picture. I'm just trying to go back. Hold on.
Because you said only the low energy part is localized, and I don't see clearly what's low energy.
So here, so this is all simulation pictures, right? So it seems that that particles that are after a long time, you according to the simulation, you get an excess of particles sort of below 1 per or k below 1 in the channel.
Okay.
Right, and so that would be the fraction of particles that is really localized.
Because in the experiment we have the feeling that everything, I mean, no particle goes through, so that's why I'm confused.
Yes, right. In the experiment, the simulation shows here a bunch of experiments, a bunch of atoms still going through. I'm trying to get rid of my thing here because I can't see this part of the screen. All right. How do I go back? There we go. So the in the simulation here, you see that there is that the atoms that actually make to the drain is actually only a very small fraction. That most of these atoms are actually being stuck in the channel, and but there's also some atoms that are the really slow atoms just get eventually get reflected by the channels and remain back in the source, in the source reservoir.
Okay, we have another questions we have still two other questions. I'm going to ask the people to put very quick question and very quick answers in the sake of interest of time. So Pierre, you have a question, and then Sergey.
Okay, thank you. So thank you for the talk. I just wanted to ask you about the ridge lines of the localization landscape in the figure.
Yeah.
There are two different colors, and I'm not sure if I missed if there's why is there two different colors for the ridge lines, or?
These are the blue lines is where the ridge actually goes down, and the red lines is where the ridge goes up.
Okay.
If you understand what I'm saying.
Okay. Okay. Thank you.
Okay, Sergey. Sergey, do you hear me?
Your microphone, Sergey.
Sergey, your microphone, you have to unmute.
Yes, now you hear me, I think.
Yes.
Yes.
Okay, yeah. So I have two related questions. The first one is about loss. Do you lose atoms in your experiments for condensate? Because this also can lead to exponential decay. And the second one is about the exponential decay itself, because in your experiments, the exponential decay, I would expect it for a given energy, but you have distribution of atoms in integers. And to add different distributions with different energies and different localization lengths, this will not necessarily give an exponential decay in space.
Yeah, so in answer to your second question, this is true. That will not necessarily give us an exponential decay. However, we do seem to eventually, at the end of the day, see an exponential channel profile, and of course, this is something that so it's not necessary, but if the distribution of atoms is relatively is odd, as it were, but for a distribution like we have, you still end up with this exponential decay. And I sort of missed your first question.
Are you sure that this exponential decay is not just losses of the atoms from the condensate?
Oh yeah. It's well, if we can certainly have nothing in the way, and these atoms will just happily be captured by this whole by the dumbbell structure, just like you see on this in the picture on your left, when there is only a very limited number of scatterers. Eventually, after a long time, and we've left it on for longer and longer, these atoms just fill up the entire dumbbell.
Okay,
So,
thank
okay,
you.
thank you.
I think that is that's certainly not it.
Okay, so let's thank Maartin again. So thank you for this very nice talk, despite the hour.
Thank you.